question in this video is, what are the components of an electric circuit? Now, just as water current is the flow of water molecules, electric current is the flow of electric charge. Electric current is defined as how fast the electric charge moves in a circuit. The higher the electric current, the faster the electric charge moves. In circuits of metal wires, electrons make up the flow of charge. This is because one or more electrons from each metal atom are free to move around the atomic lattice. Protons, on the other hand, do not move because they are bound inside the nuclei of the atoms that are more or less locked in fixed positions. So if we have a wire here, we have these electrons in the metal that are free to move around. These would be your valence electrons that can kind of move from atom to atom. And how fast they are moving is referred to as the current. It is how fast the electrons are moving. The unit of electric current is measured in amperes or amps. We abbreviate that with the letter A. However, the symbol for current is not the letter C, it is the letter I. We don't want to use the letter C because C stood for Coulomb, but where does the letter I come from? Well, the letter I comes from when they first started talking about electricity, they talked about the intensity of the current. And so the letter I stands for the intensity of the circuit. Now, the current in a circuit tells us how many electrons pass through the circuit each second. So if we look at here, just kind of one reference point, how many electrons pass every second is really what the current is referring to. So therefore, if we double the current, we double the amount of electrons that pass that point every second. There's two different types of electric current that we're going to discuss later, and those are alternating current, which is abbreviated AC. And in alternating current, the electrons are going to first move one way, and then they're going to turn around and move the other way. And so they alternate the direction they're moving. They flip-flop back and forth. The other type of current is direct current. In direct current, or DC, the electrons are always moving in one direction. We'll discuss a little bit later, but alternating current comes from outlets, and direct current comes from things like batteries. Now, if we have electrons moving, the question is, what is making these electrons move in the first place? I mean, electrons just don't move on their own, and there's electrons already in the wire. So what makes the electrons move is the voltage. The voltage is kind of our power source here. And so it is what is pushing those electrons along. Batteries and generators do this work of pushing the negative electrons away from the negative terminal and towards a positive terminal. Batteries do this through a chemical reaction, in which case typically the zinc within the battery is going to react with the acid, and that is going to create one part of the battery to be positive and the other part to be negative. And so we call this positive part the positive terminal and the negative part the negative terminal. Generators are going to do this through a process of electromagnetic induction. They're going to spin a wire close to a magnet, and that's what's going to make one side more positive and the other negative. And so in the wire that is connected, the electrons are going to move away from the negative, they're repelled by the negative, and they're going to move towards the positive terminal. The unit for voltage is the volts, and the symbol for voltage is V. Some common or typical voltages in a car battery, your voltage is going to be 12 volts. In different batteries like a double A, or a triple A battery, your voltage is 1.5 volts. And then for an outlet, which works a little bit differently, the voltage of that is going to be about 120 volts. We say that it's a root mean square voltage, but we can address that at a later date. But it's about 120 volts. So we have these first two components, the current and the voltage. The current is how fast the electrons are moving, and the voltage is what makes the electrons move. We refer to the resistance as what is preventing the electrons from moving. You might ask yourself the question, well, if we're trying to get the electrons moving, why do we have a resistance at all? Well, the resistance is from the device itself, like let's say the light bulb. Moving electrons are worthless to us. Moving electrons don't help us at all. So what we have to do is we have to convert the energy from the moving electron into something more useful. And what the light bulb does here is it steals the electron, it steals the energy, from the moving electron, and it converts that moving energy of the electron into light energy. So it's simply changing the type of energy from the motion, the kinetic energy of the moving electron, into something more useful. Some things will use this energy, like a heater or a stove can use this to convert it into a heat, which is a type of energy. We can convert this into motion, like in a fan. We can convert this into sound, like in a speaker. So the idea here is we're going to steal the energy from these moving electrons and convert it into something more useful. Now, there are certain devices like resistors. They're called resistors because their only objective is to slow the electrons down. Another problem is if we have too much electricity running through this light bulb, it's going to burn the light bulb out. Or in another device, it could create so much heat that it's going to melt the wire and create a short circuit, which could possibly cause a fire. And so what we do sometimes is we put things in the circuit called resistors, and they are going to simply slow the electrons down to a safe level. Now, wires themselves also have resistance. And there's 4 factors that affect the resistance of a wire. And again, we're going to go into a bit more detail on this later on when we talk more specifically about resistance itself. The 4 factors that affect the resistance of the wire are length, width, temperature, and material. A shorter wire has less resistance than a longer one. A thicker wire has less resistance than a thinner wire. A colder wire has less resistance than a hotter one. And wires made out of copper have a very small resistance compared to other materials like aluminum because copper is an excellent conductor. And by a conductor, I mean it allows the electricity to go through it. Now, the wire itself is surrounded by an insulator, surrounded by like a rubber or a plastic, and that does not let the electricity go through it, and so therefore it doesn't go into your hand and harm you. The unit for resistance is the ohm, but we don't use the letter O to represent resistance. The problem with using the letter O is if I have 8 ohms, if I say 8 O, that looks like 80. So instead we use the Greek letter, which is omega. It almost looks like an O, but that represents ohms. The symbol for resistance is the letter R. Now these 3 things are related to one another through something called Ohm's law. And the relationship here is that the voltage is equal to the current times the resistance. So for a given circuit of constant resistance, current and voltage are proportional to one another. This means we'll get twice the current if we have twice the voltage. The greater the voltage, the greater the current. But if the resistance is doubled for a circuit, the current would be half what it would be otherwise. The greater the resistance, the smaller the current. That makes sense. If you prevent the electrons from moving, they're going to move at a slower clip.